The insertion sort approach is that when we have an input of a set of unsorted values like this, what we do is that we just simply look for the element which is out of order. For example, we begin to scan the input, the original sequence of values, and find out that 10, 18, 25, and 30 are all greater than the previous element, so they seem to be in good order. Then we find 23, which is out of order. So the 23, of course, has to be relocated to be in front of the element 25. So what we then assume inside this algorithm, that this is already sorted and this remains to be sorted. So this is the plan. We need to move this over here and shift these two elements to the right. So what we do here is that we simply copy this into a temporary value. So we need the copy of the temporary value. So now this element is available for modification. And we modify this element by simply copying the previous element into its position and the previous element to its position as well. And we're doing it until we find the element in front of which we need to make our insertion. So after making the copy, we have overridden 23 with the new value 30, because this is where we replaced it, and then of course 25, and now we have two copies of 25, and the final step here is to replace this 25 with 23. So now this sorted list is no longer by one element, and the unsorted list is now down to one less element. And so we're going to continue this sort. Of course, the next step is that we're going to identify the value 17, and of course we're again going to make a temporary copy of it and keep copying and copying and copying to the right until we find the element which is no longer greater than 17, and therefore we will insert it in front of 18. So this will be sorted, and so forth. We can continue our sort through the end of the list. So this is an example of the insertion sort algorithm. Once again, it takes in this example we provide Java array of integers, and we specify the length of our sorting sequence that we want to execute, and this is an implementation of this insertion sort algorithm. So the complexity of this algorithm is known to be, we can compute it by using this formula. So the insertion sort makes this many comparisons during the execution, and roughly about this number of item assignments. So again, if we have a list of 1000 items, then to sort the list, the insertion has to be making about 250,000 key comparisons. Remember, in the previous example, we had 500,000 key comparisons, and now more assignments. So if the assignment is not very expensive, then this also may be a more attractive type of sorting. So these are two examples of popular sort algorithms. And so binary search is relying on the fact that the list of items is already sorted. So the search item, the item that we're searching for, is compared with the middle element of the list. And then the logic is that we have this list of items right here, right? So we have a list of items, and we compute roughly where's the middle element. And we compare these two values. So this is the search item, right? So we compare it. And because the requirement for binary search is that the list of elements is already sorted, all the items are already sorted, basically, if the item is less than the middle element, then we don't need to search the remaining part over here, and vice versa. If this item is greater than the middle element, then we don't have to search the upper part of this. And of course, as soon as we find the middle element, the search is complete, right? Because then we will find the middle over here, and we will find the middle over here, and eventually somewhere middle element will be exactly the same as the item that we're searching for. So this is an example of the binary search, right? Again, this time the requirement for binary search is that we should not forget to sort the input before we attempt searching for the value. And this is an example of searching for integer 75 in this specific example of numeric values. And the list length is 12 items, and we find the middle element as element number 5 with zero-based indexing right here. And we decide, of course, that this portion of the list is no longer of any interest, because definitely our item 75 has to be located somewhere in the remaining list. In the worst case scenario, of course, if the item is not present, it'll take the longest time to search the entire list. And this is an example of binary search implementation. Just remember that when we specify the input parameter for this binary search implementation example right here, just remember that the prerequisite, the condition that has to be true before we attempt to do our binary search is that this list has to be sorted, and only then this algorithm will produce positive results. Otherwise it will be useless, because that's the requirement for binary search, the sorted container or sorted list of items for which binary search will proceed rather very quickly. So in general, the binary search is said to have logarithmic complexity, and this is the formula by which you can find out how many comparisons you need on average to be able to find an item in this list. And the n value right here is the size of the input on our list.